Now, on the second handout, you'll notice that there is a lot more information on here. There's 6 columns. Notice that again, this one is titled Molecular Geometry, so it's a little bit different than what we saw a minute ago with our electron domain geometry. These first 2 columns, electron domain geometry and three-dimensional arrangement, these actually come pretty much are word for word for whatever it is we saw on the other page. So again, this is the second page here. Notice again that they are pretty much the same as pretty much the information you get from the other handout, so the other molecular electron domain geometry. So that kind of gives you a frame of reference. Now, within each electron domain geometry, you have several sections. With this electron domain geometry, you have a couple of sections. With this one, you have a couple of sections, and so on and so forth. So just recognize, again, this information is basically, again, the same as our other handout. Let's go and take a look at some of the other columns. Right here, the number of bonding domains and the number of electron pairs and radicals. So this essentially, again, is the representation of where my atoms are around my central atom. So if I look at the formula type, which one of those letters would be represented by the number of bonding domains for this column? That would definitely be X. So go ahead and label this X if you need to help you keep track of that. This next column right here, number of electrons. Oh, by the way, this X also goes over here too. Right, that column also works on the back. Number of electron pairs and radicals. This is again how many lone pairs there are around the central atom. So looking at my formula type, which letter represented that? Hopefully most of you figure this one out. This would be your E. Right, that's going to be the E. Okay, and remember that the X plus E gives you the number of electron domains, which is right here. Right, so again, if you look at this column right here, so 3 plus 1, that's equal to 4. 2 plus 2, that's equal to 4. The next column then is your actual answer. Now, if I asked you for the molecular geometry of certain things, I would expect you to give me the verbal language, or at least the actual text language here for each of these. Now, you kind of notice some similarities here. So if I have my three-dimensional shapes based on my molecular geometry, sometimes they look exactly identical to the electron domain geometry. But, for example, this one right here, this one's not quite the same. This one, again, is three-dimensionally like this as my molecular geometry, and its electron domain is the same. But if you look at another one in the same category, the same section here of electron domains, notice that one of them isn't quite the same geometry. This one is trigonal planar, and this one's bent/angular. Why is it bent or angular, even though it comes from the same electron domain? Well, that's because, remember that one pair of electrons takes the place of an atom, as you saw in previous examples. So in this case, it's just bent. It only pays attention to the actual atoms that are present, not the entirety of the molecule. At least not all the electron domains. So again, just the atoms that are present, not all the electron domain places. That's why molecular geometry is just a little bit different than electron domain. Right here, notice you have tetrahedral, so that appears once more, just like the electron domain geometry, identical term. But then the next one is trigonal pyramidal, meaning one of the atoms has been replaced by a lone pair. So this lone pair now has taken the place of the atom, so it takes on a new shape where we only look at the atoms that are present, and that'll be your trigonal pyramidal. Trigonal meaning triangular again, and a pyramid just within that little area. Finally, bent or angular again with this one and this one both becoming lone pairs. You now only have a bent shape, which is represented by these 3 atoms that remain. Same rule applies as you go through these, as you kind of go through more and more complicated shapes. Now these shapes again are actually a little bit more complicated, and we'll address kind of ways of how we can memorize this. By the way, we are going to have to memorize this whole thing in case you didn't catch on that earlier. But with this right here, trigonal bipyramidal, this right here is your same molecular geometry as the electron domain. But again, as you start changing out atoms with lone pairs, you see more and more differences in the shape. This one's called seesaw, so you probably can't really see it too well. But if you imagine, if this was like sort of kind of perpendicular to where it's supposed to be, these 2 are the legs that touch the ground, and this right here and this right here are the seats where they kind of go back and forth and seesaw this way and that way. T-shaped, literally just a shape of a T, like that, right? It's T-shape. And then right here is linear. Kind of notice where they're pulling or they're starting to exchange. As you go through these, all the atoms that they're taking off kind of come from the horizontal plane, right? So this right here is kind of flat, whereas this goes up and down. These up and down ones kind of are left alone. So you kind of look at this one here is removed, and then one of these two are removed, again, still in the same plane, one coming out, one going in. And this last one where all three of them are removed. So all right, and the last set here is octahedral. Octahedral here has a bunch of different shapes. But notice this one's a little bit different when they start removing from the vertical ones as opposed to the side ones. Now this one here is octahedral. Octahedral again meaning 8 faces. Square pyramidal, meaning it's a square base that has one vertical part that makes it pyramid. And then the square planar, kind of cut off on my screen. Square planar is where you have just the 4 here that basically makes a flat square. Now, determining electron domain geometry, you kind of see these here, and you'll have the chart that you can refer to. But these examples that we saw earlier, in this case, we have to look at the geometry that both the bonding domains and lone pairs take on. Since this one was, again, an AX4, this one only has 4 electron domains. Because it has 4 electron domains, again, 4 X's and no E's, this one will have the tetrahedral electron domain geometry. This one right here, NH3, this is your ammonia. It was an AX3E. This one, if you look at the domain geometry, electron domain geometry, this one again has X plus E equals 4. So its electron domain geometry, looking back at the chart, with 4 electron domains will be tetrahedral. This example right here, this formaldehyde, it had the formula type of AX3. AX3 then has 3 electron domains, again 1, 2, 3 electron domains, so that would be trigonal planar. Back to the example on the handout, this one right here, it has H2S, it had a lone pair up here, lone pair down here, and this one again had the formula AX2E2. So if you were to, again, get the formula type, look at the formula type, you can figure out how many electron domains there are. In this case, there are 4, because of 1, 2, 3, 4. Also, 2 plus 2 equals 4. Same logic to get the same answer. And that will gives you, again, tetrahedral once more. Now, molecular geometry. This one does take into account only the atoms. You kind of ignore the lone pairs for this one. So the lone pairs on this one are not part of the molecular geometry. In this one right here, we had 4 electron domains, but all 4 of them are atoms. So if you look at the second chart on the molecular geometry handout, this one would have an X of 4, E of 0. So the molecular geometry would be tetrahedral. On this one right here, this one, notice that again, even though it has 4 electron domains, one of them is a lone pair. So with 3 bonding domains, right here, and 1 lone pair, this becomes trigonal pyramidal. This example right here, this one has, again, 3 bonding domains, no lone pairs around it. So if you look on the molecular geometry handout, this one will also be trigonal planar. And back to the example on the handout, H2S. This one, all right, let's try that one more time. Let's see, back to the handout, you have the S, the H, and you have both of these. And if you, again, look at the structure here, back to our formula, or back to our formula type anyway, there's 2 bonding domains, so that's represented by this one, and then 2 lone pairs, which is represented by this and this right here. So if you look back on the molecular geometry handout, find the 2 bonding domains, 2 non-bonding domains, and that'll give you the bent, or if you want to, angular. Okay, and again, that's not butte, a really bad spelling of beautiful, it's bent. Moving on. Bond angles, these are actually going to be related to each specific type of geometry as well. These are the three-dimensional shapes, and they have a very specific set of bond angles. If you look back on the electron domain handout, on the reference tables there, the very last column gives you the electron domain angles, and this also technically applies to the molecular geometry uh, 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 angles as well. And you should also be able to find which specific ones are relevant to which angles. So you can kind of see with these right here, for example, these actually are pretty straightforward. This one again has 4 electron domains. Sorry, excuse me, it has 4 electron domains, and this angle is usually reported as 109.5. This one right here, this is actually a formula type of AX2, and that means you have a linear molecular geometry and also electron domain geometry. So this one will be reported as 180 degrees for a straight line. And this right here, since you have a 3 bonding domain compound, you're going to end up making this, looking at it, and you're going to see that this is actually 120 degrees, right? Kind of what you expect by splitting a circle into 3 equal sections. Now again, recognize that just because you draw it a certain way doesn't mean that the shape will also be that. So just by looking at this and saying that it's a straight line does not mean this is linear. We know that this is a bent compound, so you have to pay attention to what the molecule belongs to when you look at electron domain and molecular geometries. One more thing I also just want to mention here, we also like to look at bond angles according to the axial versus its equatorial. Axial means on an axis, so in this case it's that vertical line right here for this fluorine and phosphorus. Whereas equatorial refers to, along the equator, so kind of like, around the middle. So these fluorines right here are drawn, so that written anyway, so that they're around the middle. So when you look at the electron domain geometry handout and find the bond angles for fluorine for this type of thing, it's trigonal bipyramidal, and it gives you 2 reported values. Well, the 90-degree part comes from this right here. So this section ends up being your 90-degree one. Also kind of going backwards with this fluorine, that's also 90 degrees. And also right here in front, this is also going to be 90 degrees as well. But then the 120 degrees comes from the fluorine itself. So the fluorine, this right here, this is 120 degrees. This right here between this fluorine and that fluorine is also 120. And then this one right here in front is another 120 degrees as well. And of course, then this little diagram it shows you where the trigonal pyramidal is. So this is the pyramid up here on top. There's another pyramid underneath that goes behind the paper here. And then that makes it a triangular trigonal bipyramidal. Okay, so for the sake of practice, let's go ahead and take a look at these 4. You can see, again, I'll kind of give you a moment here to take a look at the actual structures here. But I'm asking for the electron domain geometry, the molecular geometry, and the bond angles of each of those. Just take a moment, you can pause it here, and then you can figure it out on your own and see how well you do compared to my answers. And you see that this is now our answers. So for carbon tetrachloride, this first one right here should be tetrahedral for both electron domain and molecular, and the bond angles here are 109.5. For NH3, I've also included the formula type there so you can compare. It's tetrahedral for its electron domain geometry. It's bent molecularly, or angular, whichever one you want to use, with 109.5 degrees. For the I3 minus, the triiodide, you're going to have AX2E3 as your formula type, and it's going to be electron domain of trigonal bipyramidal, and then it's going to be a linear molecular geometry. The bond angle on this one's a little bit different, since we do know that the bond angles for any molecules that have all of its atoms present, it would be 90 degrees and 120 because it falls under the trigonal bipyramidal electron domain geometry. But you also have to be attentive to what is actually present. Since the atoms are the only thing that's visible here, you should recognize that it's a straight line, it's linear, and that would be 180 degrees. So writing down 120 and 90 would not be fully correct. And then finally, you have trigonal bipyramidal and seesaw for SF4, and that's going to be 120 degrees and 90 degree angles between each of your atoms. So that one still maintains its electron domain bond angles.